So let's start first with the force. So when you want to find the force of this linear charge density on a test charge that you have placed at P, you have to follow certain steps. So let's talk about those. Steps to follow. Step number 1. Divide the rod into small elements of length dz and define your coordinates as x, y, z. That means I have to find, I'm defining my small area dz, say here. Number 2, choose a charge element dq defined as lambda dz for this element that you chose. Number 3, find df that corresponds to dz. How will I find df? I can use Coulomb's law. And Coulomb's law says df will be nothing other than k q0 dq over r squared, where this is r, this I can say is theta, this distance, can I call it y? So may I write cosine of theta as y over r? May I also write this r as y over y squared plus z squared square root? Now, step 4, I have to find F, right? I have to find the force. In order to find the force, and since force is a vector, I have to take into account its direction. So in order to take into account its direction, may I write dfy as df cosine of theta, where dy is this element. What is dfx? 0? It's pointing towards us, right? And what would be dfz? Again, that's along the coordinate axis, so it'll be 0. So the only one that survives is dfy, and the direction of it is along the y-axis. Okay. Oh, and these should be vectors. Sorry. Now, may I replace the value from A into here? May I also replace the value of cosine of theta into here? What do I get? KQ0 DQ over R squared Y over Y squared plus R squared square root.
Would it be a y squared plus z squared?
Oh yeah, sorry. Yeah, perfect. Yep, it should be Z squared. Thank you. Now, may I replace this R squared as well? And can I also replace this here? The DQ here. Okay, so will this expression then become K Q0 lambda dz y divided by y squared plus z squared 3/2? So it's 1 plus a half, which is 3/2. Everybody got that? So put this in a box. Are we done? Nope. We now have a dfy that corresponds to dz, but we wanted to find the total force, correct, of the whole entire thing. So how do we do that? Step 5, integrate, right? To find the total force, we will integrate. Integration of dfy kq0, lambda is a constant, y is a constant, integration over dz divided by y squared plus z squared 3/2. My limits of integration will be from minus L over 2 to L over 2. The integration of this in my book looked like this. So what will this become for us? When I plug these in, on this side, I will have a force, and I will have a K, Q0, lambda y, z, because that's what I'm integrating over, divided by y squared square root of z squared plus y squared. My limit of integration goes from minus L over 2 to L over 2. Now I have limits of integrations. May I plug them in? Oh, wait, one of the y's goes away. So I will get divided by y L over 2 z squared plus L over 2 squared square root minus L over 2 z squared plus L over 2 squared. What is L over 2 plus L over 2? Just L, right? The denominator is the same. May I rewrite this as KQ0 lambda over Y times L over wait, hold on, this should be Y. This is my bad. This should be y, right? Because y is not what we're replacing. Because in here, we're replacing all the z's with the limits of integration. I'm going to replace this value again. What was lambda? Q over L? From here? Replacing, replacing, replacing. What do I get? KQ not Q over YL L over y squared plus L over 2 squared square root. Or L's will go away. KQ0Q over y square root of y squared plus L over 2. That is the force you're going to get. For the limiting case, when y is much, much larger than the length, this will be reduced to KQ0Q over y squared. Or basically the Coulomb's law.